which explains how electromagnetic induction works. Now, this is an absolutely crucial idea in physics. It's also one of the ideas that has given rise to the birth of electricity, and the modern world you know around you is all based upon the ideas of electromagnetic induction. So let me first of all give you an example. Essentially what happens is, it's not that different from the motor effect. Remember, the motor effect was making use of the idea of having a magnetic field and then adding to that a current, and that gave you motion. Now this time it uses all the three same ideas, however induction uses again a magnetic field. You then supply some motion to it, and then that provides a current or a voltage. So you're actually creating electricity. Let's show you a little bit more clearly how that works. Let's imagine we have a simple magnetic field like the ones we've used before. This is a nice uniform magnetic field. There it is. And inside I'm going to place a wire. Now we have a north face and a south face. My piece of wire, of course. And I'm going to pull the piece of wire down through the magnetic field. So what we have is, we have the magnetic field that's been set up, we give it the motion, and we create a current. If you can imagine, the field lines are doing this, north and south, then what's happening is, as you pull the wire down, you're pulling it through the field lines. So, in order to induce a current, or we could call it a voltage if you like, because actually one in the same, it's more precise to use the word voltage, so it's probably better, though the analogy is better if we use current, but let's say voltage. So in order to induce a voltage, a conductor, which could be a piece of wire in this case, needs to cut through magnetic field lines. And this is one of the simplest methods to describe, to show how that happens. Okay, we'll look at more complicated methods a bit later on, but okay, how do we achieve a greater voltage? So in order to achieve a greater voltage, to induce, what do we need? Well, there's a few things that we could do. One of them would be to use a stronger magnet. Another one would be to use more coils of wire or more pieces of wire. And finally, and this is probably the new idea that we're coming across, you could cut the field lines faster, so you move faster. And that's a really important last point. Okay, a subtle idea that I want to bring up at this point is that it's about cutting field lines that's important. So let me show you a situation where we're not cutting field lines. Here's the same setup that we've had, our south, our north. Here's my piece of wire, and this time I move it across. Now this is, of course, my field lines haven't changed direction, of course, they're still the same. What's changed is the direction. This time the movement follows a field line. So, what should I say? Therefore, no voltage is induced. Remember, we need to cut field lines. This situation is not cutting a field line. So that, very simply, is electromagnetic induction. In actual fact, it's the reverse of the motor effect. Now, obviously, it seems quite simplistic there, but with a little bit of engineering, we can change this into something which produces very reliable voltages and very predictable behavior. And that is it's a generator. So we're going to look at generators now. So here's the engineering for a generator. It's very, very similar to an electric motor. And there are different forms of generators you can have. However, the most useful one that we know is the AC generator. And the AC stands for alternating current. So this is setting up an alternating current generator. Okay, let me explain a little bit more of how that all works. Here, once again, is my nice standard magnetic field, uniform magnetic field. And this time, a little bit like before, I'm going to have a coil of wire set up in my magnetic field. Okay, this will be rotating as it moves around. So one side will be moving up, and the other side will be moving down. So I'm providing the motion. Now it could be just me, turning it around with a handle, or it could be a propeller that's causing it to go around, think wind generation, or it could be a turbine driven by water cascading down from a high height, or it could be steam being heated by coal driving through a turbine, or even nuclear power that's heated the steam that's driving the turbine. However, you're trying to create that motion. If you're providing the motion, you can generate the current, or the voltage, to be more precise. Providing the motion is actually the kinetic energy. So let's take a look at how we connect this up to a circuit. Now there is no split ring commutator in this instance. We have solid rings, and each ring is connected to one side or the other of the coil. This is called a slip ring. And each of those in turn has a brush connected to it. And then we get connected to an external circuit. Okay, so this is a brush. But it doesn't matter, as that continually spins, this slip ring is constantly in contact with that brush. In other words, this part of the wire is constantly in contact with that brush. Okay, now let's try and talk about each phase of its motion. Let me draw. All right, now that's going to change to a nice two-dimensional drawing. I'm going to draw the north-south, and this time I'm going to draw, it's like noughts and crosses. The box will indicate one side, and the circle will indicate the other side. And there is my first setup, the first position that it's in. A little bit later, of course, it's going to move around a bit, and we're going to reach the second position, which is here. And then, there's my south side. And then we're going to move around a little bit more, a little bit of a greater rotation this time. And there's the south. And we're going to move a bit more this time, a bigger jump. North. And let's go straight across to the other side. And then finally, we're going to move across to the upright again. Right, now in each of these situations, let's just talk about what's happening, which direction it's going in. Let's look at number 1 first. So number 1, this side is going up, this side is coming down. Now if you think where our field lines are going, north to south, are we going to be cutting magnetic field lines here? Well, yes, and you're cutting them quite a lot in this situation. What about number 2? Well, let's think about the motion. This is still going up. This is still going down. There is our field line. So once again, you are cutting them, but now it's moving sideways a little bit. You're not cutting them as quickly. You're moving more or less sideways. What about when we get to the top? Here are our field lines again. But now we're moving in the direction of the field lines. So in actual fact, number 3 means that we're not going to get any current generated. Now, for number 4, here are our field lines again. But now, this side, which is the circle, note the other side, is actually moving down, so it's doing the opposite to what it's doing here. So whereas the current would be generated one direction, it's suddenly changed its direction. And finally, number 5, we've got the motion again, but this time it's in the same direction as the field lines, hence no current is generated. So here we have no current generated, no current generated. We have a maximum, or sorry, let me say a maximum at this point, and because it's going the opposite direction, we should say a minimum in this point, and somewhere between. Okay, there is a good way of predicting which direction something will flow in. However, you do not need this knowledge for the syllabus. However, I will write it down. It's called the right-hand rule, just like the left-hand rule. And the right-hand rule is for generators. Right-hand rule for generators. So in essence, we've got our 3 fingers again. I drew them terribly last time, so I might just hold off on the drawing and just use nice arrows. First finger is the field, thumb is the thrust, and second finger is the current. So without going through this in too much effort again, just very briefly here, my field is that way, my motion is up, so therefore my current is into the page. So let's just assume it's into the page there. And it's out of the page in this position. As we go around, it's still into the page, it's still out of the page. Let's move around. It gets to the top, nothing happens there, so I'll leave that blank. As it comes back down, it must be doing the opposite to that which it did originally. So therefore, we have a little dot. And then, as it comes around to the bottom again, nothing happens. So, let's look at the other side. It started to come out of the page, the dot. It continues to come out of the page. Nothing happens. As it cuts back through the field lines, the opposite effect happens. And then as it gets to the top, nothing happens. Now that might look a bit confusing, but that makes sense. We go from maximum to nothing to minimum to nothing, alternating current. So let me draw a picture of how this might look. So over a period of time, we're looking at the voltage, interestingly, in volts, time in seconds. So this is the output from the AC generator. The AC generator goes from, let's look at where these points 1 to 5 are linked to here. Maximum, point 1. This is aligned, cutting through maximum field lines. Let's look for minimum, nothing at all. So that's number 3, point 3. This is number 4, a minimum. And then number 5, nothing happens again. Number 2 is somewhere between. It's not cutting as quickly the field lines, but it's still cutting the field lines. Let's go through it again. And then from 5, we go back to 1 again. 1, 3, 4, 5, 1, 3, etc., etc. So that is the plot of an alternating current generator. And I hope you can understand why those points are as they're shown. Okay, let's do 2 more plots. One will be, what happens if I rotate it half as fast? It's going around half as fast. 2 effects happen. So if we change speed, 2 effects. 1, you change the number of oscillations per second, or the frequency. And number 2, so the frequency, that's important. We're looking at year 9 work there. The second point is you change the amount of voltage being produced. Remember we said on the first bit here, if it moves faster, it's a greater voltage. Okay, so let's first of all go half as fast. If we go half as fast, then we're only going to get half the voltage. But it will only cover half. It will take 2 wavelengths to make the same of 1 wavelength. It's terrible English, but well. So here is the plot for half speed. Okay, what happens if we move at double speed? Well, let's assume that is double the voltage. And this is somewhere double the voltage. It's going to occur 1 wavelength in half here, so we're going to go right up to the top and down to the bottom again and back up and repeat that process this is 2 times the speed. A little bit messy there, but hopefully that explains what's happening. Half the speed, twice the speed. Good. So very, very finally, what I want you to do is just go through again how you would generate a current, because those types of questions come along often. So how would you generate a current? So generating okay, so here's your standard answers. You could write it as bullet points, but ideally not, but this is what you need. You need a conductor moving through a magnetic field. You need to be crossing through field lines. Okay, that induces a voltage, the voltage first, which when connected to an electrical device or even a circuit induces a current. So conductor moving through a magnetic field, crossing the field lines are essential. It induces a voltage. When it's connected to something, induces the current. Fantastic. If you understand that, you've got it down to a T.